Okay, so we're going to be going over some homework here. We're going to go over the conceptual questions in the textbook, starting with number 1, which asks about the transfer of charge. And so we've just gone over this last class. We know it's the electrons that always move between atoms or within the atom, right? The electrons are in constant motion. The protons are stuck inside their nucleus. It's always the electrons that get transferred, no matter what. Always, always, always. Even if an object gains a positive charge, it's not because it gained protons, it's because it lost electrons. Taking a look at number 4 here. Why is it transferred by electrons? Well, it's because they're already in motion. Remember, protons are stuck inside the nuclei, and they're really, really, really far away on the atomic scale. You just watched that video of those girls demonstrating that, and that's, just a visual representation of it. We have to shrink that on down to the atomic level. Those electrons are really, really far away from the nucleus. They're still attracted to them, but they're easily plucked away, or more ones are added in. It doesn't change anything about the entire atom. What's in between the nucleus and those electrons? Well, it turns out it's nothing. It's actually empty space. And so when you were watching that video with the girls demonstrating on the track, you want to imagine that between the nucleus, that little candy, and where the girl is standing at the end with the electron, there's literally nothing in between. Nothing. It's a vacuum. There's literally nothing in between filling up the space of an atom. And so it turns out that atoms are almost completely empty, which is crazy to think about. Again, we're really sort of messing with your mind, right? And so if you were to take all the atoms in your body and squeeze them down so everything was touching each other, so that there's no empty space between, you would fit in the palm of someone's hand. That's how much nothingness there is in you. You are empty. I'm not saying your soul is empty. I'm not saying you're bad people or anything like that, but there's a whole lot of empty space in your atoms at the atomic scale. All right, let's take a look at the Cutnell and Johnson focus on concepts here. Taking a look at number 1. We have this transfer charge. They have the same amount of charge. And so we know we're going to be using the law of conservation of charge here. Hopefully that's where you started, that there's a total charge in the system of negative 10 microcoulombs. And when the charges all settle in, so they have the same charge, we can't change the total amount of charge in the system. It says there's two objects. They're each going to get negative 5 microcoulombs. So we can say that the first object loses negative 3 microcoulombs to the other object. But if you stop there, you didn't read carefully enough. It didn't ask for the charge. It says how many electrons. So at this point, if you didn't do that, you pause the video and take that extra step to find how many electrons were transferred to make this happen. So this is similar to what we had done before. We're going to take, for the number of electrons, the total charge transferred and divide by the charge per electron, which in this case is negative E, right? Remember, so micro here is 10 to the negative 6. That's the total charge transferred. This is the amount of charge per electron. You can see the units work, so electrons swing to the top here. And we do the math, we should be getting 1.88 times 10 to the 13th electrons. That is your actual answer for focus on concepts number 1. Again, if you stopped right here, you didn't read carefully enough. And as an honor student, I would expect that you would have seen that and not stopped right there. Let's take a look at number 2. All right, so we have these different interactions among the objects. What are we going to do? Well, I like to draw this out. So here, for example, are objects A and B, and it says that they attract each other. Here's objects A and C. They also attract each other. The question is, what's happening with B and C? So I'm just going to arbitrarily say maybe A is positive and B is negative, which means they would attract each other. I'm not sure if that's exactly what it is, but this certainly would work. And then A is still positive, and if C is attracted to it, C must also be negative. And this then leads us to our understanding that if we look at B, which is negative, and C, which is negative, well, they're both the same. They're going to have to repel each other. So it's got to be choice B. And of course, if you did it the other way, if you had B, A is positive and B is negative, A is negative and B is positive, you go through the same logic, you're still going to find they repel each other no matter what. So it doesn't actually matter what the charges are, just these interactions are what matters. We're speaking letter B. So this brings us to an interesting idea that it didn't matter what the actual signs of the charges were, they should interact in similar ways. So let's go back to our notes page here with the fun with balloons, right? So with the fun with balloons and the demonstration you saw in the video, we rubbed the balloons on our heads, and I told you the electrons went from my head onto the balloon. What if they did the other way? Let's go through a little experiment here, a little thought experiment. What if when we rubbed the head on the balloon, electrons went from the balloon onto the person's head? So now we can see that the balloon is positive and the head is negative. Let's see what would happen, right? So here's our two balloons, and we just did this. So we know that the blue balloon is positive, but we did the exact same thing to the red balloon, which means it also lost electrons. It is also positive, and a positive and positive would repel each other. And of course, that's what they did. We saw that happen in the video. What about the balloon and the head? Right, the balloon lost electrons, so it is positive. The head gained electrons, so it's negative, and you put them near each other, opposites attract, and of course that's exactly what happened in the video as well. And so you see there's no evidence whatsoever which way the electrons actually went. If electrons went the other way, we get the exact same results. That's a very interesting idea, but I'm telling you I'm not lying to you that way. When we rub the balloons on our heads, electrons really did go the other way. Electrons really did go from the head onto the balloon. So how do we know it goes that way? Well, it's all about what sort of objects they are, what sort of materials they are, whether they are conductors or insulators. And so this is on the back of that notes page, or the second page of that notes page, that chart here comparing conductors and insulators. Words you've probably heard of before, and you probably have some experience with this, but let's break it on down. The real definition about conductors and insulators, the difference between them is how they hold onto the electrons. We say conductors have a weak hold, insulators have a relatively strong hold. Now, as soon as I say that, some students get confused. It's not that conductors don't like electrons and insulators do like electrons. It's just something about their materials. The conductors have a weak hold on electrons, insulators have a strong hold, and when we get to chemistry, you'll learn a little bit more about this, but for our purposes, this is all we need to know. And of course, this affects their ability to conduct. Conducting electricity is really just about the passage of electrons. And so conductors, of course, have a good ability, which really just means they allow charges to pass through easily. Charges can enter and leave conductors easily because they have a weak hold on them. Now, a lot of people say insulators don't conduct electricity. That's not really true. We really say insulators have a poor ability to conduct. All that really means that they do allow charges to pass through, but it's not easy. It takes effort if you want to make it happen. It's not a natural sort of thing. And to help you visualize this, I like to liken this an analogy to parenting styles. Let's imagine we have two families, the conductor family and the insulator family. So we look at the conductor family. The parents there are kind of laissez-faire, devil may care about their rules. As long as the kids are safe, they kind of break the rules once in a while. It's not the end of the world. So let's say, in normal times, students, their kids go to school and then they're supposed to go home on the bus, and the parents realize they didn't go on the bus, and they're a little bit worried about them, so they text them, and the kid says, I'm sorry, I forgot, I had soccer practice, I'm coming home on the late bus. And the parents say, okay, you texted me, it's all good, and you let me know, you're safe, that's fine. And then a couple minutes later, the kid texts and says, oh, can I have so-and-so over for dinner? And the parents say, yeah, sure, no problem, I didn't know about it, but I'll just set an extra place at the table. And they say, ooh, can I have the entire soccer team over for dinner? And the parents say, sure, in fact, let's have a party tonight. And all right, and so they have a party at their house, and kids are coming and going. Maybe a house like this, maybe your house is normally like this, obviously not when we're doing social distancing, and maybe there are kids constantly coming and going. That's the conductor house. Kids come and go easily, charges go in and out easily, that's a conductor. Let's talk about the insulator house. For the insulator family, the parents are a little more strict, right? So they meet their kids at the bus stop, even when they're in high school. They meet them there, they walk them home. As soon as they get inside, they close the door behind them, and there are 17 locks on the door. The kids are locked in place, okay? So at 3:30 doing homework, 5:30 dinner, 7:30 in bed, lights out every night. They're very, very strict, and they adhere to these rules. That's the insulator family. If the kids want to have a friend over, they actually have to get lawyers involved, because once the friend is over, they are now part of the family. They are adopted. Once they're in, they're in. If their kid wants to leave and go to a friend's house, they say goodbye, don't come back. They're out. Once they're out, they're out. So they can get in and out, but it involves a lot of process. It's a lot more difficult to get in and out. So, if the kid wants to get out and sneak out, maybe if there's a branch that leads to the room, they can very quietly open the window and sneak out, they can do it. Or maybe they tie some bed sheets together and rappel out their window. The point is that it's not easy to get out or in, and that's the idea with insulators, that they have a strong hold on their electrons. Once they're in, they're in. Once they're out, they're out. Charges can pass through, but it's not a very natural thing. It's not an easy sort of process. Okay, let's talk about some examples of these different materials. And so in general, what make good conductors? Hopefully you know most metallic elements make good conductors. Maybe you don't know what are some of the best conductors. In class I would ask you for your ideas, but if you just sort of think of what circuits are made of, hopefully you came up with some of these. And copper is one of them, Cu, and most wires are made of copper. And it turns out Ag silver and Au gold, these are the three best conducting metals. Copper, silver, and gold. In fact, you might notice that some wires are gold-plated to help with their conductivity. Going over to the other side, what sort of materials make good insulators? Well, if most metallic elements are good conductors, most non-metallic elements are good insulators. Now, I'm saying most for both of these because there's a whole spectrum of conductivity. That a lot of metals are good conductors, but there are some metals that just aren't. A lot of non-metallic elements are good insulators. They don't conduct very well, but some of them actually conduct pretty well. So I put the word most here to indicate that, there's a whole spectrum of them. All right, what are some other good insulating materials? Just pause the video and think for yourself. Maybe write down a couple of ideas on your notes page. All right, the next one most students come up with is rubber. You probably learned that before, but there are a lot of other ones, and I'm not sure if I'm going to get all the ones that you would have said, but paper is usually one that comes up, or wood, paper is made of wood, and then cloth and glass. And you might notice that things that we build structures out of and things we make clothes out of are good electrical insulators, because it turns out things that are good thermal insulators are usually also good electrical insulators. What are some other good conducting materials? Maybe pause the video and write down some ideas. Well, we already covered metallic elements, so hopefully you didn't write down any more metal things, but a lot of people may realize that water is a good conductor. Maybe you learned that before, but we need to qualify that. We'll say tap water or rainwater or salt water are good conductors, but as it turns out, pure water is a good insulator. Now, when I say pure water, that's not bottled water. In fact, if you're looking at your bottled water, if you look at the label, you'll see it says minerals added for taste. And you might say to yourself, well, water doesn't have a taste, except when water doesn't taste good, so that means that water must have a taste to it because when it tastes good, right? And so what's happening here? Well, as water goes through your tap, through the pipes, or falls through the atmosphere as rain, or is it in the ocean, there's salt dissolved in it. As it goes through here, things dissolve, the minerals in the pipes dissolve in the water, or minerals in the atmosphere dissolve in it, and when the minerals dissolve, they break apart into ions, and ions are charge carriers. And so water that has these things dissolved in it is a conductor because it has these charge carriers in it. But pure water, sometimes what's called deionized water, has these ions removed, and so it doesn't have a charge carrier in it, and so pure water is an insulator. Okay, now we know that water is a good conductor because anytime you look at your hairdryer, on the cord there's this tag there which shows a hairdryer in a tub full of water saying, don't dry your hair in a tub full of water. Now, I'm not sure why you're drying your hair in a tub full of water, but you shouldn't do it, because if you do and drop it into the water, you're going to get electrocuted because your tap water is a good conductor. Or during the summer, if you're outside in the pool and there's a thunderstorm approaching, your parents say, get out of the pool, and they're right, because if lightning were to strike the pool, you're not getting out of the pool, well, at least not of your own volition, because the water will conduct electricity to you. But pure water, turns out, just plain old H2O is an insulator. So I guess if you've got gallons and gallons of pure water, you want to fill up your tub and then dry your hair in the tub, I guess you could do that, although I'm not really sure why you're doing that, but I guess you could. Okay, then usually students want to know about air. So pause the video and think about that for a second. When I bring up air, a lot of students bring up the idea of lightning, which of course is electricity. Electricity, as lightning passes through the air. But then I would say, does electricity happen all the time? And hopefully you recognize it doesn't, right? It only happens under certain conditions. And so air, it turns out, is actually an incredibly good insulator. Otherwise, every single time you turn on pretty much any electrical device, anytime you activate an outlet, there'll be lightning just shooting out of the outlets. That just doesn't seem to happen. Also, you may consider when you build a circuit, which I'm sure you've done in previous courses, you have to make contact between the metal of the wire and whatever else is metal for charges to flow. What's in between those wires before you make contact? Air, right? And so air better be an insulator, otherwise if air were a conductor, all electrical circuits would be on at all times. And that's just not a good idea, right? So air is actually one of the best insulators around. It's incredibly insulating. Alright, so there's these questions here, which refer back to the video you saw. I want you to pause the video, consider the ideas, and write down your answers. Okay, so hopefully you were thinking about this in terms of evidence. What let you know which is the conductor, which is the insulator. And so when we have this debate in class, usually there's good evidence for either one, but it all comes down to what had to happen with those balloons to get them to be charged. And you notice that the balloons were not just touched to mine head or Sammy's head, we had to rub them on them, which means we had to force the charge onto the balloon. Our heads lost the charge, the balloons gained the charge, but we had to force the charge onto them, and so the head acts as the conductor, and the balloon acts as the insulator. Now, we also could sort of cheat a little bit. We know that balloons are made of rubber or plastic, which I forgot to put on here. Plastic is another good insulator, and so rubber is a good insulator, and so definitely the balloon is the insulator. But in general, people, as it turns out, are good insulators, which is weird because here we're saying the head, or part of you, is the conductor. Well, it's all kind of relative. When you were in sort of electrical contact with a really good insulator, you're probably going to be the conductor. You're going to conduct better than that really good insulator. However, if you're in contact with the wires of a circuit, which are really good conductors, you are definitely the insulator. In general, people are more insulating than conductors, but as with everything, there's a spectrum of conductivity.